So in order to figure out the pH of this sulfurous acid solution, we first need to write out a reaction that describes how sulfurous acid, a weak acid, will interact with water. It's worth noting that it is in a battle with water for one of its ions, its hydrogen ions. And so when water is able to take away one of those, we will get HSO3 minus and H3O plus, which is the hydrogen ion essentially, which is what we use to calculate pH. A useful tool for these equilibrium reactions or reactions with weak acids is an ICE table, which stands for initial concentration, change in concentration, and the resulting equilibrium concentration. So we start out with our initial concentration of H2SO3, 0.211 molar. We're going to lose a little bit of that. We don't get complete dissociation because it's a weak acid. And so we'll call that little bit X. So the equilibrium concentration will simply be 0.211 minus X. Water is just going to continue to be dominating the solution. It's a mostly water solution, so the concentration of water is not going to change. So that's a big slash there. We can ignore it. HSO3 starts out at 0. HSO3 minus starts out at 0 molarity. We're going to add a little bit of that due to the 1-to-1 mole ratio. We're also going to add a little bit of H3O plus, and this is where our H3O plus is going to come from for our pH. The equilibrium expression is always the product of the products of the reaction divided by the product of the reactants concentrations in the reactions. Again, we can ignore water. Its concentration will stay constant, essentially. Plugging in our equilibrium concentrations, we get X squared over 0.211 minus X, and that's equal to the equilibrium constant Ka1 for the first dissociation. You could use a calculator. You could graph it. There's a solver function on most graphing calculators. At the end of the day, it's just a quadratic equation, and you come out with the fact that X, this little bit, is equal to 0.0477 molar. That's going to be equal to our H3O plus concentration. Now, if you consider what happens next, you get some HSO3 in the water, which can interact with the water to give us some more H3O plus. But when you run through the same process, like we did, starting with a little bit of H3O plus, you end up realizing that the concentration of H3O plus that is added is very, 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 very minimal. In fact, the starting concentration of H3O plus was 0.0477, and Ka2 is on the order of 10 to the negative 8th. So it's about 1 million times smaller than this starting concentration. So even if you run this through your calculator and solve for X, which I did, you're going to see that you end up with so little H3O plus concentration being added that when you go to calculate the pH, if you just use your initial 0.0477 molar H3O plus added from the first dissociation, you get a pH of 1.313214811621, which rounded to 3 sig figs is 1.321. If you do your calculation for pH, including both H3O plus concentrations added together, you don't get a difference in pH until you get all the way down to this digit, this first 0 after the decimal place. That was a 6 before, now it's a 0. So effectively, that is not going to move the needle much on your pH calculation. So at the end of the day, for many diprotic acids, not all, the pH is really dominated by the first dissociation, Ka1.